Now we begin looking at sequential logic design. And to begin with, let's talk about what sequential logic is and compare it to what combinational logic is to see the differences. So if you remember what combinational logic was, is the definition of it was that the outputs of the system would depend only on the instantaneous values of the inputs. So very simply, a block diagram might have, let's say, 3 inputs. Let's call them X, Y, and Z, and an output F. Anytime there was a change on any of the input variables, the output would be updated. And this was a very simple concept, but it was a very important one because the signal flow, as drawn like this, was basically inputs to outputs, and there was no notion of storage in this. So it was the output was a simple, expression that depended on the instantaneous values of the inputs. So now if you look at what a sequential logic circuit is, this is one in which the output depends on not only the instantaneous values of the inputs, let's say this X, Y, and Z again, but it also depends on past values of F. So, or past values of the outputs and also past values of the potential inputs. So you might have F past, and then you might have, continue this down here, you might have X past, Y past, and Z past. So you're basically going to have an output which can make a very intelligent decision on what its current value should be, because it not only looks at the current values of the inputs, but it's able to look at past values of the inputs and itself, and basically look at the history of what has happened within the system. And so the sequential logic nature of this is that it's a sequence of events, a sequence of inputs, and a sequence of situations that have led up to the current value that F has. So this is the primary difference between combinational and sequential logic. Now, whenever you have sequential logic, you have this notion of past values of the inputs and of itself. And so you say, well, how am I going to look into the past and figure out, what happened before I make the decision on what my current output should be? Well, that is accomplished through a storage device. And we call these sequential logic storage devices because they can be created, because they're using the sequential logic circuits, but you can actually create them with basic gates. And so what we're going to do is we're going to start looking at how you actually use basic gates to create a storage device. And we're also going to, and then we're going to start with a very simple, system that'll store ones and zeros using a cross-coupled inverter pair. And then we're going to work our way forward and go through a series of incrementally more sophisticated storage devices until we land on the ultimate storage device, which is used today in almost all circuits, which is called the D flip-flop. So what we're going to start with, though, is the concept of a cross-coupled inverter pair, and then introduce this notion of metastability. But we had to start talking about sequential logic and combinational logic and what the difference is, and that motivates the need for a storage device. So when we look at a sequential logic storage device, it's not as difficult as it first appears to store information, because we are going to limit the values that can be stored to simply a 0 and a 1. So it doesn't have to have a giant record of information. It's simply going to store a 0 and a 1. So let's consider the following circuit. This is going to be called the cross-coupled inverter pair. And let's just say let's just say I took an inverter and I drew it as follows. And then let's say I took another inverter, drew it down here, and then let's say that I took the output of one inverter and routed it back to the input of the other inverter. And then let's say that I took the output of the other inverter and went back to the input of this inverter. And let's go ahead, since we have two of the same basic gates, let's name them. So let's call it U1 and U2 just to keep them clear. And what I want to do now is let's give the outputs a name. Let's call this Q, and we'll call this Qn, and we'll see why we do that in a second. So what I want to do is I want to look at can this type of topology actually store information? And remember, all we're trying to store is 0 and 1. So let's just put a test signal in here. So let's just come along and let's just say that I forced that net right there to a 1. Well, let's follow the feedback path through. So okay, 1 goes through an inverter, becomes a 0, and then 0 is fed back to here, it's a 0, and then the 0 is inverted and becomes a 1, and that 1 comes back here and it reinforces. We actually have stored this. So if I put a 1 right there, you could say that the output is storing a 0. And if I just walk away and don't touch anything, so I forced a 1 there and then I walked away, I have stored 0. It is holding a 0 there. I don't have to do anything. I don't have to have any inputs into this system. It will just simply store a 0. So that's good. It can store half of the situation. So let's do, or half of what we wanted. Let's do the other case where I have, I'm going to force it. I'll start at forcing with the other value. So let me draw the cross-coupled inverter pair again. And let's say that this time I had a 0 that I forced there instead of a 1. So let's follow the feedback path. So 0 to a 1, it was inverted, became a 1. 1 then became a 0. And then, no, 1 was driven back here with a wire, and that's a 1. 1 went through that inverter, became a 0, and then 0 came back here and reinforced itself. So this also stored information. It's stored a 1. So you could say that this is storing now a 1. Well, that completes the task that we wanted to do, which was build a circuit that could store both a 0 and a 1. So as long as you have the ability to force a value into this cross-coupled inverter pair, it will store a piece of information, and it can store a 0 and a 1. So this is fantastic. We have a very simple device which can store 0s and 1s. Now let's take a look at the outputs. Notice that Q right here, we could call that, let's define that as the output. So Q is going to be the term we use, or the variable name we use to talk about the output. We can define the other output as Qn, and we put an N by it because it's always the inversion of Q. So notice in this situation when we're storing a 0, Qn is a 1. So it is the inversion of Q. So it's Q naught. And then when I come down here, when I had a 1, Q is storing a 1. Well, Q naught was storing a 0. So it indeed is accurate to say this is the inversion of Q. So I actually can, in this topology, I can have two outputs. I can have Q and I can have Qn, and that becomes very handy because when I start using these outputs to drive other circuits in the system, I don't have to inherently put an inverter on Q to get Q bar. It comes from the actual circuit itself. So this is the fundamental storage topology used in all sequential logic storage devices. It's a cross-coupled, and that means that I have two gates where I cross-couple them. So this is the cross-coupled configuration. This one is the inverter pair, but we'll make this more sophisticated as we go. It is a positive feedback loop, meaning that I take the output of one system and I drive it back to the input of another circuit in that same system. So there is this positive feedback notion in here, and so I have a loop of information. I actually have this loop that's being formed there. So you'll hear all those terms when you talk about describing this cross-coupled inverter pair. Okay, so now let's talk about a concept or an important concept when you have positive feedback in a digital system, specifically the cross-coupled inverter pair, and that is this notion of metastability. So if I come along, metastability, and what metastability is it is a system which has this built-in behavior that it can exist in an unstable state that's highly unstable as long as it's not disturbed. And then it takes only a slight disturbance to move it to a more stable state. So the classic example of this is imagine you had a two-dimensional hill, okay, and you put a ball at the top here. So this ball, actually, it doesn't have to be two-dimensional, it can be anything. So imagine that this ball is sitting on top of this hill, and it's a very steep hill. So if the wind blew this at all, it would go somewhere else. So if you think about this, what are the states that it's in? Let's make it a two-dimensional hill just to kind of bound what we're talking about here. So if you talk about the states that this can be in, a state being a stable position for the ball, so it's not in motion, it's not transienting or in a transient. Well, if you think about it, the ball could cruise down here, and you would have a state right there, and it's very stable, so this would be a stable state. And you could also cruise over to this side too, and that would also be stable. And if you think about it, this is also a state, okay? So it can sit there, but it's a very unstable state, okay? And the reason is that it doesn't take very much in order to cause this ball to vacate that state. So even though it's balanced at this top of this hill, all it would take is just a little puff of wind or any sort of motion, and it would cause this thing to roll down to one. The device has metastable behavior because it can exist in this unstable state, except that all you have to do is just do a tiny disturbance and the thing will move to another state. Okay, so that's what metastability is. This is actually, the two-dimensional version here is what's called a bistable. It means there's two stable states, so that's where the bi comes from. So this would be an example of a bistable system. It does have a metastable behavior, but it is bistable. Now what we see is that this cross-coupled inverter pair actually exhibits both of these. It's a bistable storage element, and it also has metastability. So let's take a look at why it has metastability. So when you look at an inverter, the behavior of an inverter, if I plotted, let's say versus time, and I'd be right there, and I'm going to plot the input, and I'll say this is Vn, and it's going to slowly cruise up to from a 0 to a 1. And let's go to 0 to VCC. Let's start talking about real voltages since we're plotting this out. And the output will be, if it's a 0, it'll be at VCC. And what ends up happening is that as this transitions up, the output will certainly transition down and be the inversion of the input. And that's fine. Except for the inverter actually has what we call gain, and that means that the output will respond much more rapid than the change in the input. So in reality, when you look at a real inverter, it looks more like this. That may not illustrate how sharp that is, but as you ramp this thing up, the input will change quite rapidly down to its other value. So you have a slope which is much steeper on the output, and that's because the outputs are being driven by the transistors in the device. And then the input, if we ramped it up like that, the output may not respond until it got to a certain point, and then it would rapidly respond. So you have this kind of notion of what we call gain, and we can call it that little g. But it means that you have kind of a small change in the input, and that resulted in a quite rapid and larger change in the output. So if you think about it, like the change in the input was only from here to here, and the change in the output was from here to here. So I actually had a change in the output which was much greater. Now why is that important? Well, let's take a look at this cross-coupled inverter pair. So I come along and I have this guy right here, and I have this guy right here, and I have this fed back to here, and I have this fed back to here. And I want to come along, and I'm going to put this into a unstable state, okay? And the way I'm going to do that is I'm going to put this at VCC over 2. So it is exactly in the middle of a 1 and a 0. So it represents this point right here. So what is this circuit going to do? Well, it'll actually drive the output to VCC over 2, because that's how an inverter responds. At VCC over 2 will be right here. It'll be driven back to here, and then the inverter will produce VCC over 2, and then it will move back and reinforce that original value. So this is now in a metastable state. Okay, so it's in a unstable state, but it is in a state. So it is going to sit here at VCC over 2 on the outputs. However, if you move this at all, just any disturbance, so you just put just a picovolt on any of these nodes, it will cause this thing to move to one of its more stable states. So you said, well, okay, if I was able to do that, would it just sit there forever? That's kind of the question. And the answer is no. It will not stay there forever, and it's due to electrical noise. So electrical noise is the term you use to describe any unwanted signal that you have. So our wanted signal is VCC over 2, but you might have noise that is an unwanted signal, and we care about the electrical noise. And you kind of say, well, where does electrical noise come from? Well, it turns out there are tons of different types of noise in any system. You can have noise from radiation. There might be radiation coupling onto one of these wires. There might be, a very common one is thermal noise. So if a material is not at absolute zero, you have motion in the electrons of the atoms in there. So you have electrons moving around. Well, electrons current is moving, and it's, unless you have a perfect material with no resistance, you're going to have current moving through a resistance, and that will produce a voltage. So thermal noise is a very common one. There's tons of different types of noise in electronics, but it's always there. Okay, so what that means is it's always there, and it's a random noise. So you really don't have control over where it comes from or what its shape and magnitude is. But let's just look at the impact of just a tiny bit of noise being inserted onto this. So let's come along and let's just say that somehow noise was inserted on this first noise, and we'll call it Vn. And Vn is very small. Well, what's going to happen is that Vn is basically going to be superimposed onto VCC over 2, but it is going to be amplified as it goes through this inverter. So when you come over to here, it's going to go the opposite way. So if you had noise that was moving over here, for example, the output would go the opposite way. So you actually would have what we would call negative G times Vn. And G represents that it's the gain. So if you had a picovolt here for Vn, you might have 10 picovolts over here, or a negative 10 picovolts. And so it's getting bigger as you go through this device. Okay, well then that comes back to here and is fed to negative G Vn. Then what happens when you go through here? Well, now you're going to have an inverter which flips the polarity, but you're going to have G times G Vn. So you actually have more noise. Now that more noise is then fed back to here, so now you have plus Vn, but you actually have also plus GGVN, and this thing continues. So then it gets amplified again, so you have minus GGGVN, and you can kind of see what's happening. As this thing goes through this loop, the noise just keeps bigger and bigger and bigger and bigger. So where does it ultimately end? This signal, VCC over 2, is going down. This output right here, and that's the Q output, this output right here, Vn, is getting bigger and bigger. And so where does it end? Well, it turns out that it ends when this goes to a logic 0 and this goes to a logic 1, or said another way, these will ultimately go to the maximum and minimum voltages in the system, which we know is this will be ground, or 0 volts, and this will be VCC, which is whatever power supply voltage you're using. So this is an example of, it was in a metastable state, an unstable state, and it was disturbed very minimally with electrical noise, and that caused us to go into a runaway situation. You can say that the device went metastable, so it went metastable as it transitions to one of these other states, these more stable states, but it did ultimately land in a stable state. If I did this exact opposite way, where I had this and I put a negative voltage on here, just a tiny bit of negative voltage noise, then it would have the exact same thing would have happened, except that it would have ultimately ended on opposite values. So it would have been on VCC and ground. So this is this concept of metastability, and it becomes very important when we build these storage devices because we want to avoid this behavior. We like the stable states. We like when we know our outputs are zeros and ones, but we never want to put a device into a situation where we have no idea where it's going to end up. We do know that if we put it right in the middle, it will go somewhere. It's going to go to one of these two states, or these two conditions, these stable states, but we don't know where it's going to go. And in a digital system, you never build a circuit where you don't know where the output's going to go. So that's what the whole point of this is try to understand what metastability is, and then try to avoid it when we build these devices. So that's the cross-coupled inverter pair, which serves as the base element for all sequential logic storage devices.